Hello and welcome back to the Oxford Online Maths Club. My name's James and I'm joined by Connor.
Hi, my name's Connor, and I'm a second year maths undergrad at Hartford, at Oxford.
Fantastic. Thanks for coming along, Connor. And thanks for coming along, people watching as well. We've gone live a minute early, like an extra minute of maths, is what Connor just said. Nice to have you with us. If you're joining live, you can join this kind of live chat thing, which is happening. You can be on screen as well. It's me at the top, and then Connor, and then maybe you down here as well. Like, for example, here is Aaron. Chat is moderated today by Tristan. So it's me and Connor and Tristan doing things, and Aaron is here as well. Maybe you can be anonymous in Slido chat, in which case I won't read out your name, but we're using Slido partly so that people can be anonymous. That is where you can join in with things that are going on. Good. I'm going to start with some ads, just because we can. Well, hang on, maybe I should switch on this poll as well. Yes, ads and polls. That's what we do around here. So there's a poll for how is your day today, which we always do. Connor, how was your day today?
It was pretty good. I'd say I would vote a 4 on the poll. So not bad, but I want to save the 5 for the absolutely amazing days. Day was pretty decent today.
Pretty good.
Pretty good.
I've come straight from doing a maths talk for a visiting school group. Actually, 2 school groups that have been put together, which has its challenges. But I'm buzzing from showing chaos theory to teenagers who didn't know they were going to see chaos theory today.
What would you give your day?
Oh, I think it's probably a 5-star day, but
Oh, nice.
I don't know. Maybe I should be leaving space, like you say. And while people are voting, they're currently mostly 4s and 5s, but with a little bit of 2 in there as well. I'm always looking out for people who vote 1 or 2. And I want to tell them that they could be watching a different episode. What a terrible plug! What a terrible segue! You could be watching a different episode that we recorded. We've done about 100 of these now over the years on various topics. There's further reading notes on there as well. So after you've seen an episode, you have to give us a bit of time to put them together. But then after you've seen an episode, you can join in with some further reading, which has maybe got some links to find out more or other information. For example, that spherical geometry thing. In my screenshot, it doesn't have any further reading, but now it does. I went afterwards and wrote some further reading notes. So hello. So if you want to see that, you can go and catch that as well. I've got the link to the open days, although I'm told that the open day booking has now filled up for the April open days. Alternatives, there's an online open day, which is going to be a bit like this. There is going to be an in-person open day in July. And there's also a waiting list for the in-person April Maths Open Day. So if you want to get on a waiting list or get on a online thing or come and see us in Oxford, then there's an open day for that. Connor, did you come to some open days?
I did, yeah. I went to one. I think it was the April one when I was in year 12. Yeah. So it was, yeah, in real life, pretty good. I enjoyed it. Persuaded me enough to apply. So yeah, you should go. Because I think like the other thing is just kind of get a feel for the uni. Like, sure, like you learn all this information, but you also just get like a vibe of what it's like. And there's lots of like current students around. You could ask questions. Lots of like lecturers, tutors. Like it was genuinely just quite like eye-opening, and it was just nice to know that I was applying to somewhere that I was happy with.
That's good. I think visiting other universities is good. I have a story about I visited a university. I thought I was going to find out about maths and find out about that particular university, but I bumped into some maths people outside a talk or something. We were talking about maths, and then I talked to other people who were attending the open day instead of joining in with the open day, which was great because that way I learnt loads of maths. We swapped maths facts. It's fantastic. So hanging around at open days is I think, a legitimate way to find out maths and meet maths people. Right, good. The poll has come back bang on 4.0 average, so I'm sort of happy with that. There's a bit of 3-star, 2-star in there, but never mind. And hello in chat to Liz and Mary and Felicity, and also a Ginger Snap. There is a mild biscuit theme going on with people's anonymous usernames. You can set it to anonymous, or you can choose, in this case, a biscuit. Oh, and I've slightly cropped it. There we go. We'll just go like that. There we go. Good. Okay. Okay, maths time, I think. Here's what I want to talk about. It's a really big triangle. We had a big triangle last week. Here's another one. This one involves adding together small numbers. And depending on how much maths you've seen before, you might have seen this maths before. Let's go. Connor, you're going to tell me, I think, roughly when you first saw something that is sometimes called Pascal's triangle. When do you think you first saw this?
I think it would probably have been maybe when I was like maybe year 10 or 11. I mean, I'm from the UK, so that's when you're like maybe 15 or 16, I think. So
Okay. Does it come
I
up
don't.
in school maths? I can't really remember.
I think it comes up in A level briefly if you're doing like probability and like basic combinatorics, but I don't think it's like actually on the syllabus. But like probably everyone's gonna find out what it is. Also, it's just kind of cool. So like people like pop teachers probably explain it, and so it's quite famous as well. But I think
Yeah.
probably I was about 15 or 16.
So it's sometimes called Pascal's triangle, but like a lot of things in maths, it's got several names. In this case, named after lots of different people. So some people call this Khayyam's triangle. In Iran, it's called Khayyam's. It's 10th, 11th century, can't remember, sometime around there, mathematician. In China, it's called Yang Hui's triangle. Apologies for pronunciation there. And in Italy, I'm told it's called Tartaglia's triangle. So everyone agrees that this is somebody's triangle. There's not a consensus on whose triangle it is. I'm drawing it now, so here we go. Aaron and Tim in chat say it's in GCSE if you do binomial expansion in GCSE, which is a totally separate topic, right? Because it's about expansions. Anyway, enough talking about it. Let's talk about what it is. I've drawn two long diagonals of ones on the board, and the rule is, other than the ones, everything else lives underneath a pair of numbers. You put in the sum of those two numbers. 1 plus 1 is 2. Welcome to Oxford Online Maths Club. So I put right number 2 here, and then down here I write the number 3, and over here I write number 3, and I keep going. So kind of underneath each pair of numbers, I write the sum of those two numbers. And the question I would like to explore today is something like, what patterns can we find? What's going on with these numbers? I've drawn it very wide, which I regret a little bit, but I was doing this 45-degree thing, which I realise now is giving me a right-angled triangle, isn't it? So
I think it's good though, because if you're going thin, then you might like not leave yourself much room later. Like now you've got that extra gap, you've got a safety net of space. So
good.
you can, it's gonna look neat.
Oh yes, Joe, did you request this? So occasionally somebody writes in, I sort of forgot to say that. Yeah, Joe definitely wrote in to request something. Was it Pascal's triangle? Could have been, couldn't it? Could have been Pascal's triangle. What's some of my ones here? They've gone slightly off grid. Oh no, I'm just out by one somehow.
I love how you said, "Oh, it's like a big triangle." It's literally infinite. Like
It's a really big triangle. Yes, it keeps going forever. You keep going. My lines are slightly wonky. I'm going to think about that. Not too hard, but I'm going to think about that a little bit. These ones are all. They should be spaced out by. There's something's gone terribly wrong in my spacing, but I think it'll be all right. Yes, Felicity has got a pattern. So I'm going to read out patterns from chat, and I think possibly I just want people to tell me what they've seen. Oh yeah, Ginger Snap in chat tells me I have to put a little 1 right at the top. And actually adding this 1 at the top would have helped me to make it my alignment slightly off. Felicity has spotted. I heard you like triangles. That hiding inside Pascal's triangle, which is made just by adding together the numbers, I'm going to draw in some more arrows. You get this sequence down here, 1, 3, 6, 10, 15, 21, which is the triangle numbers. Connor, can you explain what triangle numbers are?
Sure. So triangle numbers are numbers which are the sum of lots of consecutive integers from 1 to n. So for example, 1 is a triangle number, 1 plus 2 is the next triangle number, which is 3. 1 plus 2 plus 3 is 6, is a triangle number, and then 1 plus 2 plus 3 plus 4 is 10. So for example, to get from 1 to 3, you add 2, then you add 3, then you add 4. It's basically, that is a triangle number, right? I think that's correct definition.
Yeah, sure. So like you've mentioned that it's the sum of some numbers. You can arrange those as dots in a triangle shape. So we've got 1 dot and then 3 dots and then 6 and then 10 and then 15. Good. Okay. And you've mentioned it's the sum of the numbers, which maybe gives people a clue as to why that's happening. In each case, to get from one to the next one, the rule in Pascal's triangle is that I add something that's over here. These arrows are coming in from this side. Look, as I work down this diagonal, this 6 is the sum of the previous thing, and also something from over here, and then this 10 is the sum of the previous one, and also some extra stuff. So I guess I can think of these as being the kind of extra stuff down the side. Very nice. Okay, good. Just going to draw arrows. Oh, I shouldn't draw that arrow because there's just ones by definition. Good. Okay. Different question, I suppose. What are these? Does anybody know what these are? So there's a sequence that goes 1, 4, 10, 20, 35. Maybe you can let me know in chat if you've seen that sequence before. 1, 4, 10, 20, 35. What's going on there? I'm going to put Connor on the spot. No spoilers if you do know what that is.
I actually don't know. Wait, let me think.
Good, right, okay. We've got a question.
I've got like a guess by how you constructed the triangle numbers in Pascal's triangle. There's like a similar thing going on here, I think, but this is the extent of my guess.
Yeah, there's some people in chat with question marks, which is what they do when they're not certain. Felicity says square shape. This is kind of impossible to do in chat, but ideally we'd have some diagrams or something. If you've got a scrap of paper or something, you might want to draw a diagram of what you're imagining. Several people have said tetrahedral numbers, which is a fancy word.
I mean, that makes sense, right? Because it's a 3D triangle, basically, and then you're like increasing the dimension by going up.
I see, you're imagining... So
like you're adding a triangle to like the triangle.
People who have seen the stream before know that I'm incredible at drawing. I can do loads of great drawing. Here's a tetrahedron, right? So a triangle-based pyramid. I'm not incredible at drawing. And I suppose the 10 is coming from 1, 2, 3, 4, 5, 6, and then another triangle above. And then another triangle at the top, if you count 1 as a triangle number, which I think we are, because it's adding on a triangle each time. Yes, Tim knows where I'm going with this. The Pascal's triangle doesn't stop there, right? So you have these triangle numbers in green, you have these tetrahedral numbers. If a triangle is the sum of numbers, a tetrahedron is the sum of some triangles. So then the kind of next question is perhaps...
Good luck. Like, you're going to have fun drawing this.
Yeah, I'm not sure I can draw this, but I suppose these are like 4-dimensional.
A hypertetrahedron or something.
In chat, Tim says pentatope, which is not a word I've heard before, but same logic as before. Says Ginger Snap. Some sort of 4-dimensional question mark triangle numbers. There's a lot of triangles in this triangle. There's a lot of numbers which are inspired by summing previous things. There's a nice link, isn't there, between triangles and summing?
Yeah,
I think
it's like
I think I'm duty bound to make sure that people have seen this like formula for triangle numbers. I think I have. What,
like the geometric thing?
There's a geometric thing. I think I sort of have to, just in case people haven't seen it before. But
to be fair, that is like the name, right? Like that's kind of why it's called triangle.
Oh no, I mean like there's a proof of maybe people know a formula for the triangle numbers, sort of n plus 1 over 2, and there's a kind of geometric proof of that, which I think I have to do because I can't really not do it at this point. Somebody's just started hoovering, so I'm really sorry if you can hear that in the background. I don't know if that's coming through. I can't remember who showed me this first, but I wish I could say thank you.
I think I saw this one when during my A-level. There must have been something like geometric, but like I don't know. It's like I find it's always hard to come up with geometric proof. Like it's easy to come up with geometric proof once you know what you're trying to prove, and you can kind of like make it in that way so it works, rather than just like straight off the bat not knowing the answer, just like put out some geometry. But yeah.
Right, so the observation is that perhaps then that triangle numbers have a formula which is n plus 1 over 2. And be for the nth triangle number. And I suppose then you learn this fact. One proof, by the way, is something like, oh, there they are. There they are in Pascal's triangle. And I know what the numbers in Pascal's triangle are. They are...
That's so bad. Like,
This is terrible.
is that even like legit proof? Like, I don't know.
Right, so I can dress it up, right? I can dress it up. It depends how you know what the binomial coefficients. These things in Pascal's triangle, these numbers that we've worked out, they're called binomial coefficients sometimes, and they are the things that turn up when you have 1 plus x to the power of some number n. You have these kind of coefficients, which relates to something about choosing, something about how you get a power of like x squared out of this, or how you get a power of x cubed. There's some sort of choice from doing the multiplication out. The relationship between that and this.
Yeah, like, it kind of relates to another pattern, right? Like, I guess the sum of each row is always a power of 2. It's like sort of related to that thing.
Yeah, so there's two facts a bit like that we could talk about in Pascal's triangle. One of them is that if you add up the numbers, then yeah, you get 1 up here as a total. The sum over here is 2. The sum of these ones is 4, and so on. I reckon chat can explain why that's going on, I think. Possibly using this idea, and possibly thinking about how Pascal's triangle works. This diagram is getting quite complicated. I want to finish this thought up here. So this thought up here was triangle numbers. You can make this rectangle out of 2 triangles, which has size n, n plus 1. This is how I remember the formula, because I'm really bad at remembering if it's supposed to be n, n minus 1, or like n squared over 2 or something. I remember it by remembering you put the 2 triangles together like this, and it's n times n plus 1. But then divide by 2, because I had 2 triangles. Okay, to finish that thought. New thought that you've given me, thank you, Connor, is that if you add up the terms in each row, right, how am I going to do this? I'm going to tidy up quite a bit, I think. Let's get these 4-dimensional triangles out of here.
Yeah, that's too complicated. Too much.
I'm not sure chat likes it very much. Let's get these 3D triangles out of here because I can't draw them. Tetrahedral numbers, good. And I think we're done with triangle numbers for now, so let's get rid of the triangle numbers as well. And the observation is that when you add up the numbers in a row, you get powers of 2. Curious, is that an observation that you noticed, or is that something you've been told before? I don't know. Is it something you could notice? I'm not sure.
Maybe by luck, but I feel like why would you be like? I just like it's like really unnatural. Like, I can't instantly tell, for example, that like the sum of the 1, 5, 10, 10 though is 32. Like you just like you have to just do it. So I don't think it's that easy.
Yeah, so maybe chat's going to tell us what's going on. I just erased all the arrows, and I kind of regret that. Oh no, I don't. I could draw more arrows in if I need to. So if you add the terms, I erased everything so I could put plus signs in. If you add these things up, then you get a power of 2, and the logic is something like, yeah, you can notice if you go and look for it, but most people won't notice it. If you're told there's something there, then you can go and prove it. There's something going on there, isn't there, about how you spot stuff. And try some really weird things in order to notice a pattern. Or maybe, yeah, it's the sum of the ways you can get to each number on the row. That is a good argument. Thank you, Anonymous, in chat. Only one question mark, but it is true. They're imagining this kind of lightning strike thing. So how does this work? I've got to get this right. So if you have a lightning bolt, pow, that starts up here and goes zigzag through the Pascal's triangle, at each point going either left or right, like a kind of pachinko board with the little pins, like a pinball thing with pegs, and they could knock it left or right. Do the people watching this still know what Peggle is? That was a really big thing when I was at school. People would play a lot.
I don't even know what that. I have no clue what that
Oh
is.
no! It's a sort of video game that's a bit like pinball with things bouncing off. Oh no, I'm old. Further reading. for the further reading, I'll put in other stuff. Anyway, so I think the person in chat is imagining this kind of lightning bolt thing where at each point you go left or right, and there are different ways that you might end up at the same point. And the number is precisely the number of lightning bolt routes that you have to go down. Because in order to get struck by lightning, if you're standing here, either the bolt was there and it zigged towards you, or it was here and it zagged towards you. So it's kind of, you add up the ways that you could have been hit if you're standing there or there, and then either the lightning bolt followed you here or it followed you down here as you run away.
I saw Joe had like quite a nice thing in chat where he's saying that like just by doing the adding way of getting all the numbers, by having two numbers above, to get to the sum of the row below, you add up each number twice. Sure. And then that's why each row is double.
I've seen this demonstrated by color coding the arrows to say each number in this row is the sum. Well, the ones are ones, but each number in between is the sum of, in purple, the thing on the left, and in green, the thing on the right. And so overall, you have a kind of green copy of all of that sum and a purple copy of that sum. So that when you add everything up, you're adding, well, again, they've been combined into these numbers, 5, 10, 10, 5, 1, but hiding in there is secretly 1 plus 4, 4 plus 6, 6 plus 4, 4 plus 1, and that's just a 1. So it contains a kind of two copies, 4 plus 4, 6 plus 6, 4 plus 4. So it's copied out your sum twice, once in green and once in purple. Oh, I should have written these bits in green and purple. Oh well. That's a nice proof that it doubles each time. Yes. Pingo. Ginger says Galton board. We've got a massive Galton board. It's that demo that maybe you've seen. People do simulations of this thing as well now, which is a little bit of full circle, but simulations with beads going down, and there's lots of pegs, and they bounce off pegs, and they end up in kind of normal distribution. This kind of lightning route.
Oh yeah, that makes sense. I've seen sort of stuff like that before when like it's like obviously it's really rare that it's gonna end up near the end, because like it would have to keep going left every time or like keep going right every time. So it's kind of like it's clearly gonna end up near the middle more often, but it being a normal is new to me. But it makes sense, right? Like
I should probably put these numbers at the bottom into Excel or something, do a bar chart. I'm going to do that really in a really hacky way really quickly to demonstrate that it's kind of normal, right? Oh, my computer doesn't like this. Oh, this was a mistake. Why am I launching Excel? Cancel, cancel, cancel. Okay, good. At home, maybe you could try a bar chart. do a nice large number of this, and the values, kind of the total doubles each time. So if you want it to be like a normal distribution where the area is 1, then you need to divide by 2 to the n. Where in this case, I suppose n is 7 at the bottom. And this gives you a way to calculate those numbers that you get in the back of your statistics textbook. Maybe this is not a thing anymore. Or this is going to be another point where I'm a bit too old.
Oh no, wait, do you mean like normal tables?
Yeah, so there's a table with lots of numbers in.
They are the thing.
Statistics. This is a thing. I reckon people's calculators can do this now as well. But you need to know, for my normal distribution, what's the probability that I'm over here? Like, I've seen something really weird happen. It was this weird, and I need to know what's the probability that something like that could come out of a normal distribution. You still have tables. Felicity has this. Good. Yep. Anonymous says, wait, this makes so much sense why it works with binomial distribution now. Hooray! Nobody ever says we're making sense. This is great. Look, we're doing a link to stats, because this, I think the table at the back is quite mysterious, right? At least it wasn't for me. There was like 4 pages of just 3-digit numbers everywhere. It was mad. It just said like if you needed to know a question like that, oh, okay, go and do that. Oh, where on earth do those come from? What is the normal distribution? Anyway, it's like this exponential. But if you know that this thing looks like the normal distribution, then theoretically, at least, you could calculate lots of it. And add them
Yeah, I
up.
mean, I guess the more and more rows you do, the more and more accurate you'll get. So,
Mm.
like, if you want to 3 digits, you just go like reasonably far down, but like your error's low, like row like 10,000 or something. That's probably overkill. But like, and then you just like
Yeah.
calculate all of them, and then you're like, check row 10,001, they're basically the same, and then you're done. Like,
Right. This is not a particularly efficient way to calculate the tables and the tuples,
no,
but
don't
uh,
do 10,000 rows of Pascal's triangle by hand.
I bet your computer can do it though. And then you can compare it with the calculator version and the stats table version. T table, Z values, yeah. I can't remember what a T table is, but Z values rings a bell to me because probably you would normalize, and this is like normal or one or something.
Yeah. I think Z is the inverse function of normal for certain values. Like Z of like alpha is a probability that it's less that a normal is less than alpha, I think, or more than alpha. I can't remember exactly, but like it's used basically. It's basically a table. So you normalize, then put in the Z, and then you go back. I think is the point.
Nice. Yes, the Z values are the things that have been normalized. Uh, okay. We should explain the link to choices and combinations. We've got so far we've done a link to sequences and triangles and high dimensional geometry. We've talked about statistics and a tiny bit of calculus because you had this idea about in the limit of doing lots of things it'll get smoother and smoother. We should probably do a link to combinatorics and choices. Combinatorics means sorry, 2 question marks in chat for combinatorics. Means maths to do with choices. Is that the etymology?
Like combinations or something, like
Combinations. Let's go with that.
permutation. I don't know. This is like I don't know. Combinatorics is really cool. Like it's
Yeah.
my favorite.
The sort of standard problem that you see at A level or equivalent is something like I haven't prepared for this at all, which is a bit of an oversight. Obviously, should have thought about this coming up. Here we are. Something like I've got 5 socks.
5 socks. Sorry,
Tough days, isn't it? Fine, okay, fine. I've got 15
what's
socks.
gone wrong? It's
Well,
still
yeah, I
odd.
mean, laundry has gone wrong, Connor. You're right. I should throw away the other one. I don't pair my socks. I just have 15 socks. I have a sock drawer. That's the set of my socks. Um, it's got 15 socks in it. I choose 2. How many ways are there to do that? How many, I suppose the question is how many pairs of socks do I have?
Yeah. So it doesn't matter. Like if you choose sock one and sock two, that's the same as sock two and sock one. Like it's just like doesn't matter like the feet or anything like that. It's literally just like I'm just picking 2 socks. How many
Yeah, that's
different
why
ways
I
can you
panicked. I panicked for a moment there and thought, oh no, you put 1 sock on each foot. I remembered how socks work. Um, that's not what I mean. I just want a pair of socks.
do?
Possibly someone said, you've got to pair your socks. You can't just shove all of your socks in the sock drawer. And I say, fine, I will create 1 pair of socks. Are you happy now? So I pull up 2 socks and sarcastically pair them together at random. How many things are there that I might now be holding? It's a pair of socks. Good. Yeah. So, yes. Aaron in chat has just discovered a formula for the equation for tetrahedron numbers. And I think they know why it's true as well. It's n choose 3. That's good. Like someone's learned a formula without having to think about geometry and without having to count any 3-dimensional shapes, without having to even go out into the 3-dimensional world. You can come up with a formula for tetrahedral numbers.
Yeah, I think it's if you can always avoid geometry. I personally find it easier just to work with algebra or like combinations or some counting argument rather than like drawing 3D or 2060 shapes. Like, it's not
Exactly, yeah,
ideal.
because we have the option of going out into 3-dimensional space and having a look, but for higher dimensions, we're stuck living in 3D. 3 is quite a small number. We're doing this Maths Club broadcast in 2D, so this is because I've got this flat screen, right, to work with. So That's even worse in some sense. I'm getting dangerously close to telling people to go outside. Right. No, stay. Yes. Felicity says, is this Enchi's R? Those are the same formulas for some of series. Yes, here we go. So something like the formula is, there are 15 socks that I might choose, as I sarcastically grab a sock out of the drawer. 14 socks for the next one I pick, because I'm holding one now, so there's only 14 left, so I go in for a second one. And now I'm holding 2 socks, and I slowly and deliberately and sarcastically pair them together to make a ball, which, because it doesn't matter what order I pulled them out, I don't want to double count these pairs as I play the first one or the second one, so I should divide by 2. And the general formula, if I've got n socks and I pull out k of them, is quite bad, but I'm going to write it all out anyway. Odds are people have seen things like this before. So I'm going to go very quiet and write down a formula where I get everything absolutely right. So n socks. Connor, you need to watch this like a hawk and tell me if I get this wrong.
Okay.
Thank you. Chat's also welcome to join in with telling me that I'm getting this wrong. So you pull socks out. If you need to choose k of them, you pull socks out, making your choices, and then you must reckon with the fact that you've overcounted. How much have I overcounted? If I pull out k socks, I'm making some sort of unholy ball of socks that's got k socks in it, and I say, right, here you go. The overcounting is because, nominate Connor.
Okay. So say it's like, so you have all of, you're ignoring, you've just got like all the socks lined up, and so it's like you could choose sock 1, then two. Say you're choosing 3, you could choose 1, then 2, then 3, or 1, then 3, then 2. So I guess it's how many ways can you order the k numbers? It's just like you want to divide by all the orders. So I guess how many is that? And I think it would be k factorial, which is k times k minus 1 times k minus 2 all the way to 2 to 1.
A different way to reach that conclusion about how much overcounting you do to make this ball of socks is, if you had to make this ball of socks, there would still be lots of ways you could make that ball of socks, because as you make your choices, you put out one of them that's going to end up in the ball, and then k choices of what that first one is. Even if you're just trying to make exactly this object, you have choices along the way, and if those all count the same, then we should divide, because we've overcounted. The divisor is just k factorial. Good. Okay, James in chat says that combinatorics is the maths of counting without counting, which is very good. Okay. Yeah, good. Okay. Some people write this as NCR, like this, which in chat you're welcome to stylize as you are with just typing NCR. Oh, NCK, I suppose, so I've used the letter K. Whoops.
I think there's another one, like what I like. I used to. So initially I was doing like that because I think that's what the calculator does, and now I do it like a vector, like in curly brackets, and I know that's what looks the nicest to me now. But it's just notation; it's the same thing. Yeah, that's what
this
I
is
did.
Some of the most overloaded notation, right? It's doing lots of different things, but I also write these with kind of some brackets around it, stacking n and k, and I just have to remember that that's not quadratic residues or a vector or a fraction in a display.
No, and you also got to be careful because if you write 2 brackets and it's like a different combinatoric thing, I can't remember exactly what it is, but like you got to make sure you only have 1 set of brackets and they're curly because it's all different. But like, if you want to be safe, just put NCK. Like,
I've also seen people write, not very often, but sometimes this kind of breaks symmetry. This doesn't reveal to you the fact that Pascal's triangle's got a symmetry, left-right symmetry. As I've sometimes seen people very occasionally write this. The rule being that you put factorial signs on these. Oh, if you like factorials, you can rewrite this with n factorial divided by k factorial n minus k factorial or something. To
Oh, I
sort of
guess
say
this is nice because then it's obvious that it's symmetrical because if you put if you swap k with n minus k, then the terms are just gonna swap, and then you're still gonna be the same value, right?
yeah, so the reason people might do this is because you might be interested in splitting n in 3 ways. So that instead of just choosing k objects to be in the ball of socks, I also choose a further 3 objects to throw out the window in disgust. And so I have this choice about making the ball of socks, and then a separate choice to throw some out the window, and a kind of third category is the ones that are quivering in the sock drawer. Please to have avoided either of these fates. And so you maybe have this way of like splitting things into 3 categories. Maybe I shouldn't have used the number 3 there, but never mind. That you could have these things. These are called so these are not really what we're doing today, but these are called multinomial. I just thought there's a chance that people in chat haven't seen this, even if they've seen Pascal's triangle, and I try to make sure everyone sees something new.
Yeah, I don't think I knew about multinomials until like in the first year or two, like a probability course, and they told us about them. But like, yeah, I think like I could kind of guess, but I didn't know the formula, and I definitely haven't seen this notation.
Well, the formula's pretty good because the formula's kind of the same. It says something like if you're being very systematic, you could take your n socks, which have 3 different fates now, either to be in the sarcastic ball of socks. I'm sticking with that part of the analogy, even though it's the weirdest bit. There's a ball of socks. Tristan in chat, I think is moderating chat, so it's the first time they saw us at university. I've got 3 fates for my socks now. And maybe a systematic way to do this would be to line them up and say, right, the ones over here at the start, where it says K, they are all going in a ball of socks. And then the next 3 are going out the window, and then the remainder stay in the drawer. So sort of line them up. And then the n factorial at the top comes from the number of ways to rearrange the line of socks ready for what I'm going to do next. And the division is just a divide by each of those things factorial. Because the things going in the ball of socks, doesn't matter what order they're in, you can shuffle those around. Separately, you can shuffle around the 3 that are going out the window, it doesn't matter if they're just going outside. And separately, you can shuffle around the ones that's in the drawer. So the formula is this sort of shape, but with factorial signs on it.
Yeah, I mean, it makes like sense as well in the way that you're kind of just doing the binomial choosing twice. Like, so say you're having your scenario where some socks you're leaving in the drawer, some socks you're wearing, some socks you're throwing out the window. You're like, okay, so first I'm going to say these are the socks that are going out the window, and these are the socks that are staying inside. And then once you've done that, of the staying inside, you can pick so then you do a binomial choice on on the remaining socks you haven't really thrown out the window. So you're kind of doing it twice by picking 3 things. But yeah.
Yeah, nice. Yes, so, and in chat, Joe says that you can use Pascal's triangle. If you think about this, spoiler I suppose, but if you think about this as a 2-stage process, first select the ones that you're going to wear, and then second divvy up the remaining ones. There's kind of 2 choices there, so you can express it as in terms of just binomial choices between 2 things. Related idea, if you expand 1 plus x plus y to the power of n, then you could just go for it. So if you have the power of n here, like 3 or something, or 5, you could just go for it, multiply it all out and see what happens. And then you get some coefficients, which are, spoilers, but trinomial coefficients down here. Or you could do it in 2 steps by first expanding this together with a binomial, and then separately expanding the stuff that you get involving 1 plus x with a kind of second binomial expansion.
Yeah, that's neat. Like, because if you know how to do one thing, then you're going to just have a harder problem. But you just want to solve that problem using the same thing you know, rather than trying to figure something else. Like, it's just a nice trick to group the terms.
Yeah. Sort of binomial, willing to do another binomial afterwards is how I might expand this if I had to. Because I know the binomial just uses Pascal's triangle, and I've kind of learned some of these numbers. I don't know. Some of them seem familiar anyway. Okay. We're not done, are we? We have all these plus signs on the board. I'm going to switch half of them to minus signs. I never know if people... I don't know if people are going to like this or not. Let's find out. Okay, half of them are switching to minus signs. So they're not going to be 1, 2, 4, 8, 16 anymore. If you put minus sign here, here, so every other one. So I'll start with 1, but then I'll put in alternating plus and minus signs. If you've seen this before, let me know. You might already have let me know. Oh no, is this spoilers for Promise? Oops. I can't remember what's on the Promise question sheet. I think Promise applications have now closed, so possibly it's not bad spoilers. Here are some sums on the board. Something you can do is work them all out. Not this one. You get 0, and then you get 0, and then you get 0, and then you get, oh, it takes a while, 8 and 8 is 0, and then you get,
wow, no way, next one's 0.
It is 0.
Wait,
have you seen this before?
No.
You've not seen this before? Okay, great, here we are. Okay, I like to show everyone something new. So you get, oh, right, minus 5 plus 15 is 10, minus 20 is minus 10, plus 15 is 5, minus 6 is minus 1, plus 1 is 0. And I'll leave the last one as an exercise for the reader.
It might not be 0. You want to check?
Wow, okay. So maybe people in chat can work out what's going on. I think I also want to get Connor to work out what's going on. Why are all of these 0 if I put some minus signs in here as well?
Yeah, I mean, like, looking at some of the rows, it seems easier. So, for example, say look at the row where it's 1, 3, 3, 1.
That one was easier for me to do in my head, yes.
That seems easier than the one below. Or the one above. So, yeah.
Yeah, okay, so you're right. Some of the rows where the row is a palindrome, the same forwards as it is. Wait, no, that's all of them. The rows with an even number of numbers are palindromic, and these things flip minus and plus signs as you read across. Everything's fine. The thing on the left has a minus sign, the thing on the right has a plus sign. Same down here. No, all the way down here, so this thing has a minus sign, that one has a plus sign. So maybe this last row is actually easy because there's a minus 7 here, there's a 7 over there. Yes, Enora in chat, there we go. So I think we talked too fast there because people were typing, but it's okay. Enora was typing yes, it's even for the even rows with an even number of numbers, you're fine. For the other rows though, it's slightly more mysterious, right? I'll take you back to this 1 minus 4 plus 6 minus 4 plus 1. I have a kind of hint, I suppose, which is to consider the positive and negative numbers separately.
Oh, this isn't what I thought you'd say as the hint. My
what was it?
So I haven't seen this, but like the way that I'm thinking about it is yeah, maybe different. And if you don't explain it, I could say what I'm thinking after, but it has more relation to the 1 plus x to the n expansion.
There is a link there. So we can go 2 routes. We can either talk about the 1 plus x to the n thing, or we can talk about relating each row to the previous row.
Yeah.
Which is a kind of induction way of doing it. I don't really know if people have seen induction before. What does chat want? Chat, shall we talk about 1 plus x to the n for this fact with the minus sign? Should we talk about 1 plus x to the n, or shall we talk about relating each row to the previous row? If you would like something different, you can also tell us in chat. We're going to talk vaguely while you let us know what's happening next.
Yeah, there's probably like other ways. Like if you're I don't know, like that I haven't really thought about. Like Pascal's triangle links to so much. Like there's definitely like going to be a choosing way, like a combinatoric way that. But how are you like minusing in picks? Like that's weird.
Yeah, so you're subtracting choices.
I mean, it could be counts, but counting you wouldn't subtract.
So because we're trying to prove that something is equal to 0 and there's a bunch of minus signs, we have the option of moving everything onto the right-hand side to get rid of the minus signs. if you do that, then in words, what you'd be trying to prove is that given n socks, the number of ways of choosing an even number of socks is the same number as the number of ways of choosing an odd number of socks.
Yeah, that's quite a
And
nice.
there is an
way of
elegant
explaining it.
counting method where instead of doing any actual counting, you explain why we can toggle between an odd collection of socks and an even collection of socks, backwards and forwards. Yes, anonymous. Oh wait, people voting in chat. Sherry in chat has voted for 1 plus x to the n. So, spoiler for that one method, I suppose. If you set x to be -1,
Yeah.
did you think of this? Was this what you?
This was my instinct, right? Because you're when you're saying the row of the sum of each row is 2 to the n, you put x as 1. So here, just put x as -1, and so that's what you're doing, right? Like,
So I'll start expanding this out with the binomial expansion, lol, which tells me that I have to do a whole bunch of things like this: 1 to the n, and then the next term has 1 to the n minus 1 and a -1 to the 1, and the coefficient is n choose 1. And then the next term is n choose 2, 1 to the n minus 2 minus 1 squared, and so on. You know how the binomial expansion goes. If you want the binomial expansion method, sorry, you keep getting terms like this. So you get these binomial coefficients, and you get, like the 1 to the n's don't matter. You get a load of alternating minus plus, because -1 squared is 1, and then it goes back to -1 again, forwards and backwards. But on the other hand, this is obviously 0, because it's 1 minus 1 to the power of n. Isn't that silly?
it's really cool. Like, because the right-hand side is like, it's really not obvious as 0. But then,
no,
like,
look. So 1 minus 4 plus 6 minus 4 plus 1. If you set n to be 4, then
it's just not obvious as 0.
The
like left-hand side, like anyone can tell you that's 0.
1 minus 1 to the power of anything you like. Except maybe 0.
Yeah,
what's going on up here?
That sounds really dodgy.
What 0 to the 0? Don't look up that. Right, okay. Yes, that's one proof. Another proof is something like each row is the sum of the ones. It's kind of sum of 2 copies of the one before. Roughly speaking, you draw in the green and purple arrows that we had before, and half of them are being added, half of them being subtracted. But it's kind of there's some sums of the previous thing, and the previous thing was 0. So I'm not going to draw them in for time, but it's related to the previous one. There you go. You picked which one we would do. Yes. Anonymous has put some things in chat which are very good, which I like. So each row is related to the previous one. Nobody's voted for it because it was out loud, but because we set it up, I'm going to do the punchline as well. For the counting socks method, maybe I'll tag Connor in. The observation was if you move the things with the minus signs onto the other side, then what we're saying is the number of ways to choose an odd number of socks is the same as the number of ways to choose an even number of socks. Did you have any ideas about how to explain that?
I mean, if I've got like some guess, but like it doesn't seem entirely correct along the lines of if you're choosing an odd number, like if it's an odd numbered row, then if there's like a total of odd number socks, then choosing an odd number of socks is the same as leaving an even number.
Yes.
Something along those lines.
That's the argument that we had with yes. So it's a good argument that like this -7 cancels with that 7 because choosing some of the socks is the same as like choosing the other socks. The same number of ways of doing that. There's a slightly different argument that works in the odd and the even cases. Goes like this. One of the socks is actually my favorite. You can't tell, it doesn't really matter, but it's made of gold. No, wait, that makes me sound even weirder than I already sound with the sock.
It's made of gold, but I can't tell, and I have gold socks.
Yeah. I've done some stupid setup here. Look, it's just intangibly my favorite. You can't tell. Forget the gold. Gold would be terrible for socks. What am I saying? It's just my favorite. So for any odd collection of socks that I see, I can make the following change. I can, if it's including my favorite sock, I can remove that sock. And if it's not including my favorite sock, I can add in my favorite sock. So there's a kind of toggle that just flip the decision about my favorite sock, including it if it's not there, or removing it if it is. That's a one-to-one correspondence between collections of odd numbers of socks versus collections of even numbers of socks. In each case, it's just my favorite sock bouncing backwards and forwards between the sock drawer and the pile. So it's a one-to-one correspondence between the odd collections and the even collections. That's a subtly different thing because it doesn't flip all of the socks. It only flips one of the socks, whether it's included or not. Good. I really like this sort of topic because you can do these arguments that are either just nuts counting arguments without saying any numbers, or just like, oh, just move one sock backwards and forwards, it's bijection. Or you can do this kind of algebra thing, or you can do a kind of induction relating everything together.
Yeah, it's neat. I think like it's quite useful to understand it from multiple ways, because then you can really think about what's going on, especially with like understanding what's going on with the socks rather than just being like, okay, so like you might be able to prove it mathematically, but like what is actually going on here? I don't know. Like maybe think about it. It's nice.
Sherry in chat says, if you flip all of the signs that I've drawn on the board, you always get 2 instead of 0, which is true. And I'm going to leave that one as an exercise for the reader. So something like here, 1 plus 1. And the observation is if I flip these, then you get 2. Sorry, these should now be 2. If you flip all of the signs displayed on the board, then you're flipping a lot of signs, and now you get the number 2 instead, in all cases. It's pretty good. I like that as well. Exercise for reader, I think. Not reader. You could be reading, I suppose. Exercise for chat. Let's go from there. Should we do the final party trick, I think? We've got about 10 minutes. It's actually something I think Tim said earlier, but I want to do it anyway. My aim is not to show something that's new to everyone. My aim is to show everyone something new. That's a kind of logical quantifiers the other way around. For each person there's a new thing, not for each... Yeah, okay.
No, it's correct.
Flashback to Introduction to University Maths, Connor.
Yeah. You got
the logical reasoning.
Converse isn't always true.
Yeah. Good times. The thing that I'm gonna do, I feel like odd numbers. Yeah, we're gonna go odd numbers. In magenta. This is the sort of thing that turns up in YouTube videos as well, because I mean, I know we're in a YouTube video right now, but you know, other YouTube videos, because it's just really nice. What I'm doing is circling the odd numbers in Pascal's triangle. So there's some rules about these, because well, we're just adding numbers together, and you know what happens when you add odd numbers together, or when you add odd and even numbers together. Obviously all these ones down the diagonal are odd. Then I've got a row here that's all odd. And it was Joe earlier. Sorry, I thought it was Tim. It was Joe. Okay. And what you get is this pattern, which is great. Let me describe the pattern. Or maybe Connor, have you seen this before? Do you want to describe the pattern? Or have we got...
I mean, you kind of have like lots of triangles, right? And then you have some like upside down triangles that aren't colored, and then like the triangles are getting bigger, but then you have these small triangles, but then you have big triangles made by these small triangles. It's cool.
So
and then bigger and bigger triangles.
So you have these little triangles that are arranged themselves in larger triangles that are arranged themselves in an even larger triangle, and this keeps happening on the way down. It's so good. Sierpinski triangle, there you go in chat. Yes, there's a formula for how many things you got. And Nora's built one of these in real life out of paper. Brilliant. I really like this. So I think this gets quite a lot of airtime on other YouTube videos or something, because Sierpinski triangle, it's nice, right? It's this kind of fractal where you have all these triangles building outwards. The thing that I would encourage you to try, and this might be a thing you could try at home, is instead of looking at the odd numbers, I would like you to look at the multiples of, I'm going to say 7. I guess I didn't need to cross out the word odd, I've switched colour. But multiples of 7, because, well, to start off with, we haven't got any multiples of 7, and now suddenly they come along all at once down here. Possibly chat can guess what happens next after that, right? Like we got some multiples of 7. I'm not going to work out the numbers for the next row because I'd have to add together 2-digit numbers. But possibly you can see what's going to happen next with the multiples of 7 underneath.
Yeah, I mean, you know, like stuff about adding multiples of numbers to another multiple of the same number. Or
Yeah,
like,
so yes. Joe's seen the recent Ben Sparks video on number 5 with this. Good. Fleur saw this in the maths masterclass. I say the maths masterclass. I think that might be an Oxford one. Good. Somebody says, how is this triangle useful? Which, if they're talking about Pascal's triangle, then great news. This is how you do binomial expansions, and it gives you the normal distribution if you go far enough. So you can do stats with it if you want to. It also tells you about counting things, and I think it's surprising that all those things are linked. So it's a good gateway for trying to understand lots of different topics all at once. Can fractals go both up and down in magnitude? Yeah, good question, right?
that's like, wait, that's actually really interesting. But surely, right? Like, if you're drawing a fractal in like a finite space, like say I just draw a square and you're like, okay, draw me a fractal in the square.
Yeah.
Like, it can't go up that much in magnitude because you're gonna get out the square.
So I think what they mean, I guess, is the first time you meet Sapinski's triangle or something is not here, probably. I mean, if you just met Sapinski's triangle, hey, look, triangles, brilliant. The first time you probably meet it is somebody tells you to start, not with the square, but with like a triangle, and then you cut out the middle, and you cut out the middle, and you cut out the middle, and you build this by removing things from a finite object, which I suppose they're thinking of as a fractal that goes down in scale.
Yeah.
The thing we're imagining here is, I suppose there exists a smallest scale, and then we're building up. Pascal's triangle keeps going on forever. It's infinitely large, so there's space for lots of activities. And in particular, we can arrange more and more copies of this thing to sort of photocopy it and print it 3 times and stick it together to make something bigger and bigger as we go outwards. I count that as a fractal.
Yeah, I mean, I guess you can also have like fractals that go up and down. Like you can have like the fractal you drew in the top left with all the small triangles in these triangles, and then you can also go out infinitely much. So
Yeah, great idea. Yeah. Place a Sapinski's triangle on each of the odd numbers in Pascal's triangle, and now you have, that's a definition of some points. Sure is some points. Do Cantor set, but all of the keep going outwards as well. Make it photocopy Cantor set and put lots of them next to each other. Yeah. So
yeah,
I've seen both examples of things where you have lots of small details and also things where you just keep zooming out and it gets sort of same thing. I guess there's a distinction that Pascal's triangle, the odd numbers, there is a smallest scale if you don't put Sapinski's triangle at every point.
yes.
Yeah, so there's some sequences here about the points where this happen. So the points where you get a full row, like bingo, it goes all the way across. There is a pattern to be found there, which you can maybe think about. I've circled those in purple, but possibly I should have circled them in red because there's a pattern of odd number things. If you've got access to a computer and you know how to teach a computer to do lots of calculations, you might find that useful. Hot tip if you want to do that. If you only care about whether things are multiples of 7 or not, then you only need to keep track of the remainders. The fact that this is 20 is it's a huge number, I might as well just store the fact that that's 6 more than a multiple of 7.
Yeah.
So if you're getting a computer to do this, don't get it to calculate the huge numbers that are actually in Pascal's triangle. Get it to calculate just the remainders. If you've met modular arithmetic, then you have heard this advice before.
Yeah, I mean that's a lot simpler, and your triangle will look slightly strange, right? Because you're just gonna have like 3 and like 6 going to 2 and stuff, but like yeah,
There's
it
a
works.
version of this where you because it's just rules, right? You don't have to use numbers. You can specify, if you have if you do the instead of ones, if you put like your favorite color in some squares going down those diagonals, you just color it in, and then you have a kind of lookup table for what to do when you see if the squares above are these colors. You can set that up so you get the rules. For example, here for like this odd number stuff, if you have 2 odd numbers, then the thing underneath is even. So the rule is just if these things are circled, the next one shouldn't be.
Yeah.
And then you don't even need to work out the numbers. It's just a rule about if the things above you match, you're not circled. If the things above you are different, then you get circled. So kind of
Yeah.
the layer there of abstraction is almost not about Pascal's triangle. Because Pascal's triangle mod 2 throws out quite a lot of information. Is there a proof for it? I think you can do that. I think you can work that out. It's a challenge for chat. Is there a proof that this is what's going on? Observation. We start with a single 1 at the top, and all of this row. So if you had a load of even numbers around here, a load of even numbers around this row, and a single odd number, then you would necessarily get this shape underneath. It kind of generates itself underneath. So if you had lots of even numbers around, this was just a small part of a bigger bit of space. For example, there's an odd number down here and a bunch of even numbers around, and it generates all the stuff underneath it until it kind of joins up with something else. So it
Yeah, I mean,
inevitably does the same thing every time.
you can kind of write it as like rows of zeros that are not there, right? Like,
Yeah, your computer might prefer it if you throw in lots of zeros so that it's got something to add, and 0 is pretty harmless as a thing to add, and 0 is even, so it
yeah,
won't show up. So then the proof goes something like, well, I know this is not a proof, but the proof is something like it works on this small scale, and then it does it again, and then it does that again, and each time there's some doubling going on, but it's just doing the same thing each time twice. Once on the left from the 1 that you write. You keep writing all these ones, and you keep triggering the thing to start again. You get this big blam, loads of odd numbers, and then you've still got some 1s on the side, and they trigger the same thing, which does this copies of it, printing out copies of the previous iteration that you had until they meet in the middle, which is precisely when it's time for you to admire a larger version of Sierpinski triangle. Proof by inherently it's repetitive, and you can formalize that by explaining what the repetition is. But this thing is bound to keep doing the same thing because there are very, very simple rules behind what's going on here to do with adding together odd and even numbers. We've gone slightly over. We gave them a bonus minute at the start and 2 bonus minutes at the end.
3 minutes is a luxury.
I know, 3 minutes. I think 3 minutes, but we're lucky to have the minutes that we have with you. Connor, thank you very much for coming on the show to talk about Pascal's triangle.
Thanks for having me on.
I'm pleased that I showed you a thing about my negative numbers and putting together odd collections of socks. Thank you, chat, as well, for joining in, especially when we hit that Sierpinski triangle. That was really... I'm glad Ben Sparks has done that video recently. I'm really glad to see that people have seen Sierpinski's triangle. There you go. Fleur said that was great. Honora says that favourite session so far. But Tim's got the sign-off line in chat, so we'll do that. We will see you in 167 hours for another episode of the Oxford Online Maths Club. Until then, have a good evening, have a good weekend, and it's goodbye from me. Bye. Oh, and goodbye from Connor.
Goodbye.
There we go. I'm terrible at that sign-off. Right, here we go. Bye, everyone.